Hello, everyone. Thanks for the great introduction. In this presentation, in the next 45 minutes or so, we're going to talk about how we can move fast, ship things faster, increase our velocity, and build things. By building, I mean adding code, fixing bugs, improving the user experience in a safe manner. But before that, the boring part, I'm Mohammed. I'm a Google developer expert as well in the Google Cloud technologies. As mentioned, I work at Spotify, a music streaming company. And if you want to discuss anything, maybe after the conference, my Twitter handle is Laytoon. Enough about the boring part. And we all know in this conference probably that the demand for speed and innovation is everywhere. Users nowadays don't want to wait days, weeks, or months to get their bug fixed, to get their new feature introduced, to get their user experience improved. They want those things. They want those things fast. Actually, they want them now. However, the dodged hand for speed might sometimes conflict with security, which favors most of the time the status quo. And if you have a security engineer in your team, you most of the time basically skip the processes, find backdoors to avoid having security, since it's kind of hold us back. However, speed alone is not enough. We all know a company that was bragging about how fast they ship things, and they even introduced it as part of their mottos, basically, moving fast and breaking things. And they ended actually breaking things in the end. And from a security point of view, it was a big miss. And I like to say that security is like air. When it's there, nobody notices it, right? It's there, everything is fine. But once it goes missing, everyone starts screaming. Everyone notices how important it is. And that's what's happened. And once security is missing, the trust that you spent years building with your customers, with your users, with your clients, basically evades. So DevOps, when it was introduced, it helped us to increase our velocity, have this two pizza team size kind of, bringing everyone to the table, having this like one view of how we want to move and how we want to improve things. And security is definitely required. Security is important because, as I mentioned, it ensures the trust that we have between us as a platform, as a product, and then our users, which is the data of our users. And that's what the DevSecOps movement tries to brings, basically. It tries to save a seat in the table for everyone, both developers, operations, and also security folks. And I hate the name DevSecOps, by the way, but I just like to set the ground of what we are going to discuss in this presentation. But as Solomon Hykes said in last year, and Solomon is basically the co-founder of Docker, the container technology, said like DevSecOps is basically just DevOps done right. So DevSecOps tries to save a seat in the table for everyone, tries to keep the developers doing what they do best, fixing bugs, introducing new features, improving the user experience. And it enables the operations to, once those features are introduced, once the artifact is ready to be shipped, ship it through production as fast as possible. And the important thing in DevSecOps and what it tries to highlight is to keep a seat on the table to the security folks as well, ensuring that they are involved not only in the development process, deployment process, but also in setting up the process, the pipeline that we set up to deploy and ship our artifacts to production. So by now you figured what this presentation is about. It's going to be about the Formula One. How many of you know what Formula One is? Okay, all the room. Good. How many of you know the Drive to Survive Netflix documentary? Few hands. Okay, so Drive to Survive appeared 5, 6 years ago, and it basically aims to tell the backstory, behind the scenes story of the Formula One. So the Formula One, basically very fast cars in a weird way that improves for aerodynamics. It has a lot of innovation in the car. It pushed the car industry and the automotive industry forward with a lot of innovation. And they have races in some weekends. Actually, this weekend there is a race in Monaco Grand Prix, and the free practice one is happening now as I speak. So this is a great coincidence, basically. But Drive to Survive, it tells in an entertaining way, in a drama way, what happens behind the scenes of the Formula One. It's good, not bad. Give it a shot if you want to have some time to kill. But I started watching it during the pandemic, basically, when I had a lot of time and we would basically lock it up in our rooms. But nevertheless, while watching the episode, this actually happened. So a driver from the Has team, who has like a team in the Formula One, his name is Roma, was driving the car with a lightning speed, 300 kilometers per hour. 300 kilometers per hour, did a bad maneuver, the car hit the barrier and turned instantly into a fireball. Now, by any measure, such accident is a death sentence, right? And what surprised me is even the Formula One folks, the people that oversees the Formula One, basically was worried about such accident. And then Roma said there, and yeah, Netflix put some drama in there, but at the end, Roma managed to get out from the car on his own, by his own feet. He got some damages, he got some injuries, but nothing much that you would expect from such a damaging and deadly incident. And that got me thinking that the Formula One folks and the FIA, which is the organization that oversees the Formula One races, must be doing a lot of things right to manage that even if the worst thing happen, the deadliest accidents happen, ensure the safety of the drivers at all times. And if we go back to software architecture, what would happen if we started designing our system, our services, our architecture with the same level of devotion, with the same level of putting the security of the data of our clients, our customers, our users as a priority while designing our systems. So while watching the episodes and throughout the whole documentary, they mention little security and they keep talking about safety. Now I'm not an English native speaker, so I use the words interchangeably. But when I opened the dictionary, I found that security means the state of being free from danger or threat. Now, in software engineering, this is not what we are actually trying to achieve. We know that from the moment we put a service facing the internet, there are dozens of things that trade that service. There are like dozens of hundreds of thousands of users that are trying to break our system, sneak in, steal our databases, steal our data, or just break the system. However, safety means the condition of being protected from risk or injury. And if you think about it, this is actually what we are trying to achieve. We know that the environment that we deploy our services, our artifact, our platform is not safe. And we build processes, we build tools, we have a lot of tools and a lot of insights there just to try to keep our service, our system, our application running in a safe manner. And that means, at least from my point of view, that good architecture should let people go as fast as possible, increase their velocity, ship things faster in a safe manner. And that interested my curiosity. So I started a journey to check the safety measures and how the Formula One and the teams in the FIA build their cars, with all the safety regulation and safety measures they put, and compare this, have an analogy on how we can build, or some patterns, some practices that we can adopt or are already there in the software engineering industry. And they ended up by 10 measures. 5 of them are basically pre-crash measures, and those are the things that the Formula One people ensure before the drivers get into the car and also before the crash happen. And 5 of them, this part, is actually the things that they do once the car crashes, when the accident actually happens. And from a data point of view, because trust only the data, it actually helped a lot to increase the security of and the safety of the drivers and the cars in the Formula One. So we can see here that as we introduced more and more regulations, the number of, let me read that, is that the number of deaths? Yeah, the number of deaths drastically decreased as we introduced more and more regulations that help it to increase the safety of one of the fastest motorsport in the world. And as you can see, the number of days between fatal accidents also increased as we introduced more and more regulations and more safety measures. So the hope here is, throughout these measures, implementing them in our software applications, architecture, we can basically help to reduce the amount of incidents, security incidents that we have. So let's jump into the fun part. Pre-crash measures. The first one is, in the Formula One cars, they have seat belts, obviously, but their seat belts is quite different than the one we have. Their seat belts is a 6-point harness, which is like, there's a kind of a round thing where there's a 6-point harness that is tailored for each driver. Like they design it to fit each driver depending on how high it is, how fit it is, basically. And the particularity of this belt, or this harness of this belt, is basically that when the driver gets into the car, he can't harness himself. He needs the help from the team basically to lock him up. However, he can release it by a press of a button. Like you press the belt and then it releases itself. And from a software, this is how it looks basically. So it's kind of different, but it battle tested, and it keeps the driver safe, since like they have a light speed. And then from a software engineering perspective, this is similar to automation, right? Or the push to deploy or push to release analogy. And you release that by having a lot of automation things, a lot of testing, a lot of building basically a process that help them to ensure automation. And automation is really important in the software engineering world in a sense that it has a lot of benefit. Automation helps to free up some of the teams from the manual work, and they can use that time that we saved from automation in order to pursue other more innovative, more creative stuff, or simply fix bugs and ship new features. Automation can help also to reduce the manual work, and we know we as humans sucks really bad when it comes to manual repetitive tasks. So the errors that might be introduced from the fact of manual work can be basically removed if we automate much of the process that we do in scanning, deploying, releasing, and stuff. And the other thing is automation can increase transparency within the team. By tracking each change, each bug fix, each security fix that we introduce into our code. And that helps to track back in time which a feature was introduced and how we fixed it basically. So it helps to have this transparency within your team. That was the first one. The second one is stringent dynamic, static, and load test to ensure the safety of the drivers. And that means that they're basically testing the car in different conditions. They test the car when it's a wet day, when it's a windy day, when it's a super hot day, And during the weeks or during the weekends, basically the teams travel to different Grand Prix, and the week starts on Friday, as in today, with free practices where the team gather data around the car. But what they do more is they basically update the car with minor changes that helps them to improve the performance of the car as they go. And from a software engineering perspective, this is similar to having a trusted, repeatable, and more importantly, adversarial CI/CD pipeline, where we are testing at each point in time, how our application will behave and react, and expose our application to the same conditions that it's going to be deployed to into production. And by having that, we ensure that our application will basically go through the same issues, the same struggle that it will face during production. And we will help to uncover those issues earlier in the process that we can fix and improve before shipping it into production. And adversarial here is really important because not only when we're introducing or having a discussion with the security folks in the development process or the release process or the deployment process, but we are having a discussion with them to design the full process end to end. And that means that we will have a continuous security testing, a continuous security improvement throughout our process. So we are finding bugs, especially security bugs, faster and fixing them before they reach production. Another thing we can do actually to have or test our application in the same environment, in the same production environment, is actually deploying it into production. And a very good practice that can help here is canary deployment, which means that we are basically deploying our application side to side with production, with like old code and new code, and converting and sending a small fraction of the traffic to a new application. And that will help us to detect bugs, detect security failures fast, and have metrics. And those metrics basically can be automated. So you can compare errors, you can compare security faults, you can compare latencies and stuff. And once those thresholds are reached, we roll back automatically. Otherwise, we consider this release is actually safe and can be rolled automatically to production. And it's really helpful since we are testing our new code in the same environment that is going to be deployed to, with the same user behaviors, with the same traffic, and with the same load. The third thing they have is the cockpit is surrounded by deformable crash protection structures. And this is actually the cockpit. And they tested it all the time, simulating the speed that the car goes through, and they crash it basically, and they check that the driver is actually safe. The drivers and the team always test in the cockpit because, like, it's the backbone of the Formula One cars. But that's to say, they are testing for failure, right? And that means that our application should be designed especially in a distributed world, for failure. Application nowadays, or system nowadays, no longer should focus on functionality only, but we should design those systems and those applications for other issues, like network outages, database failures, other dependencies failures, and so on and so forth. And some of the things that we can do to improve security in a distributed world is mutual TLS. Mutual TLS is basically an extension of TLS, also known as HTTPS, where both the client and the server are both servers. Because like in a distributed world, you are making requests in both ways, right? So MTLS here ensures that both the client and the server, both your services, are basically authenticated against each other, and the traffic is not sent. And like once the both services are authenticated and authorized to send traffic. And once that's done, once we have this authentication, the traffic that is circulating inside your cluster is basically encrypted, which adds another layer of security. Another thing we can do is implementing or adopting the microsegmented architecture. And that means we, in a microsegmented architecture, keep the data and the services owning the data as far as possible from the internet services and the internet. And that means even if an attacker manages to access one of the outlayer services, one of the internet-facing services, our architecture, he will get access to only an internet service, facing service, and the data is not there. It's basically a decorator or a domain transfer object, domain transfer service more. And our application will basically deform itself and protect itself in the same way that the cockpit will do for the driver. And that means that we are keeping the data safe, and the attacker will need to do additional work in order to get access to the data owning services. Okay, the third or the fourth is drivers must demonstrate that they can get out of the car within 5 seconds. So if you want to race and a crash happened, I want you to get out of the car as fast as possible, right? And the teams or the FIA basically says, show me that before you get into the car or before you get into the race. Show me that you can get out of the car as fast as possible before the race even begins. And you do that all the time before each practice and each race. And this is not only designed for the worst case, but this is actually testing for the worst case. And from a software engineer perspective, this is similar to chaos engineering. We, in our system, in our architecture, in our services, in our application, we all have and we all know how our application will react basically if something happens or in face of failures. But what scares us the most is the things that we don't know our application, the things that turns into incident. And fail or chaos engineering basically is a practice that allow us to test, stress our application in order to detect failure before they became outages and before they became big incidents. And it helps us to uncover what we call the unknown unknowns. And you can start with the smallest experiment possible. You can start by basically introducing latencies, sending 400s in one of the services, and then check how your application reacts. Take notes and check how basically the impact was. And then have a postmortem and design solutions and how you can improve. And then you can grow gradually, which will help to increase the confidence of your application and increase the resiliency of your application as well. Okay, so I have 20 minutes. Nice. The last thing in the pre-crash measures is constant monitoring and replacement of the tires. This is the world record of changing the tires in the Formula 1. It's under 2 seconds, more precisely 1 second, 82 milliseconds from the Red Bull team. And look how proud they are, how happy they are, and the celebration they have for not trying to patch the tires, trying to fix the tires, but actually to change the tire and replace them. Compare this to our attitude in the software engineering and hello infrastructure engineers, when we're trying to keep the server alive as long as we can. We basically, if there is a security vulnerability, we basically try to patch it. If there is an issue with our server, we try to take care of it. And that to say, there is other things, especially in the cloud era and the rise of cloud resources, that should be considered and change the way we treat our architecture. We're all probably familiar with the cattle versus pet analogy, and that basically mean we shouldn't treat our service and our infrastructure with this close relationship treating them as a member of our families, patching them, nurturing them, fixing them, probably giving them names in our VMs and services. But with the cattle, we should treat our infrastructure as cattle, basically disposable infrastructure, disposable resources, bringing them up as well and shutting them down as well. And if we accept this zoomorphic analogy, that was hard. How about pushing it a little bit further with the chickens? Especially that if we compare the time for cattle to reach adulthood compared to chicken, it's weeks for the chicken compared to years for the cattle. And also the amount of resources we need to invest for the chicken to reach adulthood and maturity, maturity is much, much less than we do for the cattle, right? And that to say, there is other metrics that would probably worth investing in chicken when we treat our infrastructure and deployment units. The first one is reverse uptime. And let's probably explain it with an example. Imagine that you have a cluster and an attacker managed to get access to one node, to a node in the cluster, right? That's by itself bad. By the attacker managed to hide his presence and uses that node to attack other base or other nodes in your system or probably outside. And imagine now you didn't uncover him, you didn't know his existence. What you can do is having after each amount of time, let's say 1 day, you can basically remove the old node and spin up a new one. And from a security point of view, you can't backdoor a system that is completely ravaged, right? This is a great win from a security perspective that if you, after each amount of time, which is the reverse uptime, basically remove the node and spin up a new one, you basically block the attacker and fix it at least intermediately or temporarily the problem, and the attacker would need to repeat the same process in order to get access to the node. Now combine that with the base image freshness, especially in the container world, and that base image freshness is basically the golden image that you use to deploy or to use for all your other services and your other images and your other containers, right? And this base image freshness needs to be constantly approved, constantly patched, constantly fixed against vulnerabilities. Now imagine that there is a zero-day vulnerability and you fix it in your base image freshness. The maximum amount of time that you are exposed is basically the amount or the reverse uptime time, right? So combining both those approaches, you ensure that even if there is security vulnerability, a zero-day vulnerability, once you patch it, you know that the maximum amount of time that you're going to be exposed is basically the reverse uptime. And the more the reverse uptime is shorter, the more quicker you're going to react to those vulnerabilities. Okay, we finished with the 5 pre-crash measures. Now, what would happen if the crash happened, if the accident happened and the driver is actually burning? The first thing they have is, following a crash, the driver is extricated from the car by lifting out the entire seat. And compare this to when a car accident happened, the driver is there in the crash scene, like thinking of his life. In the Formula One, the time is really crucial, so design the car in a modular way, enable them if a crash happened and the rescue team managed to get access to the driver and they can't get him out, they basically lift out the entire seat, pull him out of the crash scene and try to save him. And in a software engineering world, this is similar to having or design our application in a modular way. And most importantly, in a loosely coupled way. And modularity and loosely coupled systems had a lot of benefits, starting with fewer dependencies. When your application is highly coupled, the amount of dependencies needs increases exponentially. Now, if it's loosely coupled, designed in a distributed way, it needs actually fewer dependencies. It's also isolation failure. Um, you delegate some of the complexity of managing the system and keeping it alive to other teams, other services that they have to deal with other things. So isolation failure and increasing focus, because you are focusing only on the things that your application needs to do, and also evolvable architecture. You no longer need to focus on other things and focus on other things, but design also only the things that it needs, and you have this freedom to improve your application or decouple it as well and bring it to multiple instances in order to increase the velocity and the speed of your application. The second thing they do is a HANS system, and HANS basically stands for hand and neck system, that absorbs and redistributes forces that would otherwise hit the driver's skull and neck muscles. And this is basically how the hand system looks like. It's basically the black thing right there. So when a crash happens, the load, the load forces, or the amount of forces generated from the crash is gigantic. So basically, this system take those forces, redistribute them through the driver's body that otherwise would basically impact his back and neck muscles. And in a software engineering world, this is similar to designing our architecture in an elastic way, starting with load balancers. If you are having a good day and there is an increase in the traffic, you can basically have load balancers that evenly distribute traffic through the different nodes in your cluster. Having auto scaling, if you're having a very good day and your nodes couldn't keep up basically with the amount of traffic, you can basically spin up other nodes in order to increase the capacity of your system. Request time threshold, if a service misbehaving and taking a lot of time to respond, you can basically set some request time threshold, and that to free up the resources and free up the CPU. In some of the cases, depending on your business, you might want to have a degrading performance, especially for some important users. And also implementing anti-overload patterns such as circuit breaker and experiential backup helps to reduce the problems we will face if we are having a good day, especially during a cascading failure and such. The other thing is driver suits are fire resistant, and this is how our friend Roma managed to get out from the car on his own. And the suits that the drivers wear in Formula One basically can keep the driver's body under 42 degrees Celsius, even if the outside temperature is more. And it's really important to keep the driver's body in a limited or a good threshold. And it's similar to implementing some patterns that would help to keep our system in, such as implementing the least privilege principle, meaning that you give the process, you give the application the minimum set of access rights and resources, allowing it to perform its function. Defense in depth and building those multi-layers of security. So even if an attacker managed to sneak in and pass one of the layers, he would basically be blocked by another layer of security that would eventually step in. And having a zero trust policy is really important, especially in a distributed world. Having in software engineering, especially in distributed system, having no trust is better, unless they have obviously something like a key token authorization that prove their identity. So avoiding implicit trust is really important from a security point of view, especially in distributed systems. And another example is hardware security modules and HSM. And hardware security modules basically help to give you a key to encrypt or hash your your data. So imagine that you have an application, and this application you have passwords. So you have a system that's basically hash those or encrypt those passwords, and an attacker managed to get access to the database, extrapolate it, put it there, and then brute force the system until it managed to decrypt your passwords, and then sell them in the black market, and you wouldn't know. Hardware security modules, basically, whenever you need to hash a password, it would basically request a key from the system, from the hardware security module, and you hash your password with that key. Now, even if an attacker managed to get your data out of your system, he would still need that key to dehash or decrypt your passwords, right? So the data without the hardware security module is basically useless. And you are basically keeping it inside your cluster, inside your data center in order to can't get the data out. Now, this is good in a sense that hopefully you have some security monitoring tools that will help you to identify his presence and then kick him out. But this is a great way that to lock in the attacker, lock him in, and then keep him within your system until you can basically react to that. Another thing they have is fire suppression system that can be activated by the driver externally or by the RICE marshal. And notice how they distributed access depending on the scenario. If there's a fire and the driver is awake and cautious, you can basically press the button in order to trigger the fire suppression system. If the driver passes out, the marshal get there, they can click a button outside the car to trigger it. If the driver passes out, the safety team can't get to the driver, the marshal can't activate it remotely. And this is similar to the way we distribute access within our system. Be aware of be overly optimistic and giving access to everyone, and don't be overly pessimistic and basically blocking everyone and locking yourself out of the door. So having the right access policy and putting communication policies for your services and application is really important from a security point of view. And finally, Formula One are really crazy about data. They gather a lot of data from the car, and they analyze it and improve the car performance based on that. And it really helps when the crash happen, because like before the rescue team get into the driver and the doctor gets into the driver, they already know how severe the crash was and what potentially the driver would need in order to save him. And needless to say that no system should go to production without monitoring tools in place, especially from a security point of view and treating the security events, and obviously having alerting tools that in case of unexpected behavior, it will basically trigger alerts. Wanted to end the slide by this presentation by a couple of slides. The first one is this one. This is how the drivers within the Formula One car looks like. The situation is not really comfortable from a driver point of view, but it helps to achieve the best performance out of the car because of the aerodynamics and how it works. So it's all about the trade-off. Even in security, it's a balance between risks and business. So keeping that in mind is really important while trying to implement most of those patterns and improve your security. And the last slide is numbers from cost of data breach report of last year by IBM Security Files. They said that the cost of cyber attack in 2022 was around 4 million. But the second number scares me the most. It takes over 277 days to detect a data breach, which is crazy. So almost 8-9 months there that an attacker basically is in our cluster, in our nodes, and we don't know about it until the data appear in the news or in the black market. So I hope that throughout this presentation we had at least some knowledge about Formula One, but otherwise some other things that we can implement in order to improve safety, resiliency of our application. Thank you.